Good evening, everyone. It is my great pleasure tonight to introduce our distinguished speaker for the public lecture, Professor Jian-Wei Pan. And clearly, if you are in the field, you don't need any introduction for him. However, because this is a public lecture, let's make a little introduction for the general public. Professor Jian-Wei Pan is a professor of physics at USTC and also academician in the International Academy of Science. Also is foreign members of Royal Society in London. And he received many awards, including the Misius Awards back in 2019, as you've seen the other day. As you probably know, Pan in ancient Greek means whole and everything. And indeed, he seems to have performed every conceivable experiment. So all the experiments you can think of, probably has done already. So this could be, a good idea for a research project, trying to do something that he hasn't done already, or even more challenging research project, trying to do something better than what he did, right? So this is to say that he has achieved incredible results in all the fields of quantum technologies, entangling many photons together, building quantum satellites, and even achieving quantum advantage. So without further ado, please join me in welcoming Professor Jian-Wei Pan.
Thank you, Marco, for your kind introduction. Dear Gilles and dear colleague and friend, and good evening. So first of all, and many thanks for you all for flying over and far to Samya and to this nice place. But of course, I'm also terribly sorry for the bad weather, especially for the typhoon, which delayed our conference for one day. So here I would like to mention an interesting story. It seems to me quantum is always sometimes related to bad weather. So in 2016, and after the launch of the Misius satellite, and the weather in Moscow became very cold. So some of my friends asked me whether the Misius satellite could change the weather in Moscow. So I said, no, this is not something what we can secure. So, but unfortunately this time, there's some important person come to Samya, maybe and the weather become worse again. Okay, anyway, yeah, it's just for joking. So, it's so nice to meet, many old friends, and also meet some young colleagues. And which remind me I'm now already some old person in some sense. So and this year is right, and it really is a nice time. To celebrate the establishment of quantum mechanics, because we know and in this year there's so many conferences in many different places to celebrate the birth or the 100 years birth of quantum mechanics. So interestingly, I would like to mention, two joint events. So one is because in May, I went to Vienna to celebrate 80 years birthday of Anton. So I also know, and actually our pioneer, our supervisor, and our best friend, and Gilles is also turned to be now, he also 70 years old. So so my talk is dedicated to Gilles Bassar to celebrate his 70 years birthday. Okay? Now, okay. Yeah, okay. So, as we all know, since the establishment of quantum mechanics 100 years ago, so quantum mechanics has become the pillars of modern science and technology. So which have given birth to many major technological advances, which has significantly changed our life. And interestingly, on the other hand, in the parallel development, which started from the test of quantum foundation, and we gradually and develop some groundbreaking technology. So we are able to coherently manipulate quantum system. This consequently leads to quantum information science. So and quantum communication, and which can provide an unconditional way, unconditional secure way for information transfer. And with the help of quantum computation and quantum simulation, we can increase the computational power, and we can also exploit quantum entanglement or quantum superposition to gain the high precision and sensitivity. So, and we know, and typically we have two types of application thanks to the invention of Giles and Charles Burnett. So the first one is quantum key distribution, as we all know. By which we can generate a sequence of shared secret key between Alice and Bob. Then, using the one-time pad inclusion and declusion method, we can achieve a secure transition of classic information. And also, of course, with the help of the entangled-based QKD, we can also achieve secure key distribution. Of course, to me, another interesting application is the so-called quantum teleportation, by which we can transfer quantum information without actually sending the particle itself. So, with these two applications, as I will mention to you, lay the foundation of the quantum network. So actually, people often ask, now quantum key distribution already become a mature technology. So what is the near-term application of quantum teleportation? So for me, the quantum teleportation offers an efficient way to connect quantum computing terminal. And suppose, for example, we have a user who needs to transmit a task to a quantum computing terminal. And his task contains a superposition state of 100 qubits. So to perform, for example, some tasks which relate to the blind quantum computing task. So how to efficiently send this information to a remote quantum computer? So the classical way we know the size of the qubit space of 100 qubit is 2 to the power of 100. So transmitting an equivalent amount of 2 to the power of 100 bit of information, and actually this so the volume of this information is millions times the total amount of data stored in the world. So if you really want to efficiently transfer a superposition state to a quantum computing server, it's not possible to use the classical way. So for me, and with the help of quantum teleportation, suppose we can share 100 entangled pair, then with the help of quantum and teleportation, we can effectively, we can efficiently build a quantum computing network. And this, and to me, in the near term, is some sort of important application. So therefore, as predicted in a nice article published in Science a few years ago in 2021, and in this article, and our, so the author, predict, so in the near future, so quantum network or quantum and internet is coming to our everyday life. So in his imagination, so we could, with the help of quantum key distribution, we can achieve secure quantum communication, and we can also, with the help of quantum teleportation, to offer an efficient way for connection between distant quantum computer. And also, with the help of quantum sensing or quantum network, we can achieve arch-high resolution for quantum sensing. So I think this is something and is happening and also will come true in the near future. So, okay. So now I will go back to 30 years ago and review some historical experiments. So we know the first proof of concept demonstration of QKD on the table was performed by Charles and Gil together with some students. So I mean, and more than 30 years ago. And also, I was lucky enough to join Anton Training Group then in Innsbruck to perform the first demonstration of quantum teleportation of independent photonic qubit. And also, you see, so the distance is still very short, on the order of a few tens centimeters. So, and this is the first two experiments in quantum communication, QKD and quantum teleportation. So then, I mean, later and early experiments pay great effort to extend the QKD distance. And for example, and Townsend and John Reality, and they managed to send quantum key distribution over 10-kilometer fiber. And almost simultaneously, and Nicolas Gisin in the same years, and he also managed to, demonstrate, QKD over kilometer scale. So by, 2000, so Hughes already managed to demonstrate quantum key distribution over fiber and over underground fiber on a distance of 48 kilometers. So by 2005, then QKD over 100 kilometer fiber has been demonstrated by several independent groups. So however, it once again is due to Gilles. In 2000, he pointed out, and actually, due to the imperfection of realistic quantum device, and we have several security loopholes. So the first one, and for example, there are two main reasons. One is due to the imperfect single photon source. And for example, as Gilles pointed out, due to the photon number splitting attack, so eavesdrop, and one can use this to eavesdrop key with occasion to identical photon event. Then 10 years later, and Vadim and his colleague, they show another, and drawback and loophole, the so-called blind attack, due to the imperfect single photon source. In the blind attack experiments, one can fully control and detect by specially tailored bright illumination. So in these two cases, for example, due to the beam split attack, so the secure distance is only on the order of 10 kilometers in fiber. So therefore, we need to overcome two challenges. So one is overcome the security loophole caused by imperfection of realistic device. So then the second one is to overcome the exponential photon loss in the fiber. So as Nicolas Gisin pointed out, in order to achieve quantum key distribution over 1,000 kilometer fiber, and even with the perfect 10 gigahertz single photon source and ideal single photon detector, and only, one photon can be transmitted on average percentually. So therefore, we need to really solve these two drawbacks before we can promote any practical application of QKD. So, interestingly, and a few years later, and in 2005, and Hao Quan Lu and Xiangbin Wang followed the original concept suggested by Huang from Korea, and they proposed a so-called decoy-state QKD, which is secure and with one can achieve secure QKD with a non-ideal single photon source. So and which extend the secure distance from 10 kilometer to 100 kilometer. So and from the part of non-ideal single photon source. And later on, and in 2012, and Hao Quan Lu and suggest the so-called measurement device independent QKD, and which is immune to any attack on detection. So interestingly, and his idea is actually inspired by entanglement-based QKD scheme. So, and which is some sort of, in a sense, we can call the MDI-QKD skin as a post-select entanglement between indistinguishable and a photon. So, and 1 year later, and we managed to report the first experimental demonstration of MDI-QKD over 50 kilometers. Then later, and the distance is extended to 400 kilometers. But now, and due to the two photon loss, so the distance of the 400 kilometers already reaches the bit rate distance and limit in fiber. So how to exceed the bit rate and distance limit? Then, and Marcos and together with his colleague, and they proposed the so-called and twin field MDI-QKD with single photon interference. So compared to the original MDI-QKD, where the efficiency of two photon interference is proportional to eta. So eta is the square of the single channel photon loss. However, with the help of single photon interference, twin field MDI-QKD, then efficiency and can be improved up to square root of eta. So, according to the estimation, so in this and following this scheme, then the QKD in commercial fiber can even reach 700 to 800 kilometers. But of course, this idea impose significant technical challenge. If this idea was proposed 10 years earlier, then people think this idea is of no practical and useless. But luckily, and by 2020, because we already have very ultra-precise frequency dissemination technology from the quantum metrology people. So with this technology, one can achieve so the frequency difference of two and remote laser to be better than, to be less than 10 to minus 18 over 10,000 seconds. And also, the length and perturbation of fiber due to the temperature change and so on can be controlled to be less than 100 nanometers. So with the help of an advanced ultra-precise frequency transfer technology, and we managed to show the possibility to perform a twin field QKD over 500 kilometers, so from Jinan city to Qingdao city. So the whole distance is 500 kilometers. So 2 years ago, and in coiled fiber, so this distance has been extended to 1,000 kilometers. So, and of course, and to me, one of the very interesting topic is how to provide a comprehensive or conclusive solution for the security of QKD. So one of the nice idea is the so-called device-independent QKD based on R2ACT 91 protocol. So by which, and one can permit the security even without full knowledge of the underlying quantum device, as long as we have the violation of Bell equality. So in 2022, 3 independent group, and our experiment is with the photon, then there are 2 and in parallel experiments with trap ion and atom, and we manage the first demonstration of DI-QKD, but with a very short distance. And you can see in our photon experiment is 200 meters, and in the ion experiment 2 meters, and in the atom experiment is 400 meters. But of course, only the 2 meter experiment, they really achieve to generate the key with a finite size of the key. So because the distance is so short and the key rate is so lower, so a practical DI-QKD at that time, it still remains an extremely technological challenge. But of course, even without DI-QKD, as pointed out by Charles Burnett, so in the MDI-QKD, an EVOS untrusted device remain outside of Alice's and Bob's trusted enclosure. So they need only trust themselves not to have inadvertently create a side channel to Eve, through incompetent design of their do-it-yourself light source. So therefore, and by combining MDI QKD and do-it-yourself light source, so the information thread secure QKD with related device can be approached properly. But of course, our long-term goal is still to achieve practical DI-QKD, and which I will come back and later. So after having mentioned the progress or the whole and history about the security of QKD, I want to come to the second issue, how to extend the distance, and especially how to extend quantum teleportation distance and with fiber. So quantum repeater is one of the promising methods and to generate efficient, to achieve efficient in-time distribution over long distance. So the basic idea is to use quantum repeater. So the basic idea of quantum repeater is to use in-time swapping to provide the solution to photon loss following the teleportation and skin of entanglement, or in Zhukovsky and Anton's and paper they call it entanglement swapping, and actually which is a teleportation of entanglement. And also, one could use the entanglement purification protocol to provide a solution for the decoherence caused by unavoidable quantum caused by the noise, unavoidable noise by the quantum channel. So once again, so purification scheme was proposed by Gilles and Bassar, and together with David Deutsch and Arthur Eckert and so on. So the quantum repeater imposed three major requirements for the experimental realization. So entanglement swapping with high precision, and entanglement purification with high precision, and quantum memory with high performance. So the reason why we need high precision and high and performance is because if the entanglement swapping precision is very low, then that means the noise is so huge, then such a quantum repeater scheme is not a fault-tolerant quantum repeater scheme. And also, if the precision of entanglement purification is not high enough, then after purification, the quality of entanglement will even worse. So we really need to achieve high precision of fault-tolerant entanglement swapping and entanglement purification. In the meantime, we also need to achieve a high performance quantum memory, which I will come back and later. So the first demonstration of entanglement swapping with lean optics was performed in 1998. And then 5 years later, we managed to report a high precision, which is fault-tolerant entanglement swapping on a high precision 4-photon interferometry. Now the second step is how to provide experimental demonstration for entanglement purification. Because original entanglement purification by Gilles and Charles would require C0 operation between individual particles. So the C0 operation between individual photons is extremely difficult to be implemented. Till now, we're still not yet able to realize high precision C0 operation between individual photons. So interestingly, in 2001, we proposed a practical scheme. So the required nonlinearity for individual photon and can be effectively induced by post-selection. So just using lean optics, polarized beam splitter. Then 2 years later, we managed to report the first high precision fault-tolerant entanglement purification. So now for the quantum repeater, the remaining element is quantum memory. Yeah. So the reason why we need quantum memory is because in the multiple realization of entanglement swapping and purification, if without quantum memory, then the cost of results in multi-stage experiment of quantum repeater will proportional to 1/p to the power of 2m, where p is the probability for each special experimental run for the EPR source to emit one EPR pair. Therefore, such a scheme is not a scalable one. But if we know when the entanglement is generated or entanglement can be generated in a heralded way, then can store on demand, then after some time, if each pair, and if each node already have entanglement and ready, then we perform entanglement swapping and purification, then the total cost of the resource is proportional to 1 over p squared. So in this way, we can enormously improve the efficiency of quantum repeater to achieve efficient distribution of quantum entanglement between a distant location. So in 2001, and Lu Minduan, together with Peter Zoller, Michael Lukin, and Igor Sirach, they proposed a practical single photon based, which is very similar to the twin beam MDI QKD. Yeah, single photon quantum repeater scheme. But in this experiment, because the scheme was proposed 24 years ago, at that time for this scheme will require stability because this is a single photon quantum repeater scheme. Then we'll require stability of subwavelength, and which means after the two-wave packet pass through 100 kilometers of fiber, then uncertainty of the and the length should be less than 100 nanometer. At that time, it's very difficult. So people think this scheme is not visible. So we are forced to find out some better means and solution. So we are forced to come back to a two-photon quantum repeater scheme, which is correspond to original BDCZ scheme. So Hans Briegel, so and Wolfgang Du, and Sirach and Zoller. So in the two-photon scheme only requires stability of a few and a few hundred and a few 10 centimeter. So follow our scheme, with the two-photon quantum memory scheme. In 2008, we meant to report a functional node for BDCZ quantum repeater node. But of course, the problem is the lifetime of our quantum memory at that time is very short. It's only about 1 microsecond. So now the problem is to have a scalable quantum repeater, we would need these two. And these two requirements. So first, so the memory or the lifetime of the memory must be long enough so that to ensure every node to create entanglement pair. Otherwise, during the preparation of entanglement and before you succeed for all the nodes, so the entanglement already died. So that's the problem we have to solve. So the second thing is, after you have the entanglement to be generated, then you must be ensure to have a high retrieval efficiency so that the stored quantum state can be converted back into photonic excitation with sufficient high efficiency so that we can efficiently establish remote entanglement. However, according to two coefficients, so the lifetime is only 1 microsecond, so the efficiency is only 35%. So in order to, fulfill the requirement of a 500 kilometer quantum repeater, so the lifetime have to be extended about 8 order of magnitude. So we still have serious problem at that time. So therefore, and we spent almost 10 years trying to find all kind of method. So first of all, and we use the clock state of the atomic memory to avoid, so such a state is insensitive to the magnetic field. So that, and the decoherence caused by the magnetic noise can be neglected. And also, and we explore ring cavity to increase the interaction efficiency between the hard-coded atom and the retrievelator and retrieve laser beam, so that we can significantly increase the retrieval efficiency. And also, we also explored the so-called optical lattice confinement. to suppress the atom-atom collision-induced decoherence. After all this effort, so by 2016, and 8 years later, and we managed to have this coefficient, and which we have a lifetime about a few hundred milliseconds, and while with 76% of the true efficiency. So from here you can see at this point, so this coefficient is already touched the borderline, which already support quantum repeater, enabling quantum communication at a distance of 500 kilometers. Now, and what are the remaining thing we need to solve? So, one more thing and remain is to connect quantum memory node with fiber. So we have to shift the atomic wavelength to telecom wavelength, because the wavelength of our atomic memory is 800 nanometer long, but the telecom wavelength is 1300 nanometer or 1500 nanometer. So by developing the so-called frequency conversion method, we shift the atomic wavelength to telecom wavelength. So in this way, so 4 years later, and we managed to generate quantum entanglement between remote memory over tens of kilometers. So in last year, we report the first multi-node entanglement-based quantum network over metropolitan area. So to me, now we are already at a stage in 2000 similar to the quantum key distribution. Yeah. So very recently, we already managed to entanglement two quantum memory over 400 kilometers in fiber. So now I would like to briefly mention our recent result. For an elementary building block of quantum repeater for scalable quantum network. So in this experiment, we started this project 4 years ago together with Chang, and he is in the audience. And so in this experiment, and we try to generate ion and photon entanglement, Then because so the wavelength of the of the photon from the calcium atom is in 300 nanometer. Then with our telecom quantum frequency conversion technology, which convert this to 1300 nanometer. Then through a 50 kilometer fiber, and also following the single photon interferon entanglement, and we managed to show a building block, elementary building block for scalable quantum network. So in this experiment, and for example, the coherent time or storage time of the quantum memory is over 500 milliseconds, and while the generation time to have hallowed entanglement generation is about a half second. So in this way, this experiment, and for the first time, and meet the pre-request condition for quantum repeater at a metropolitan scale. So in this experiment, we also show, for 10 kilometer, and we can really generate and DIQKD, and we can rely DIQKD over 10 kilometer and with a finite size, So of course, and also because we are not sure whether ion can really work properly, so in the meantime, we also work on atomic quantum memory. So very recently, we have a similar result. So we also demonstrate a DIQKD using entangled atom, which are separated by a 100 kilometer fiber. So and you can see from 1998, after 27 years effort, now we are gradually already reach phase transition temperature, so that we can really go a scalable quantum network. But of course, in order to have a practical quantum repeater over 1,000 kilometer scale, we will probably still need 5 or 10 years. So this is what we are going to do in our mind. So the reason why we start to consider another possibility, the satellite-based quantum communication, is back to 2003. I find out the quantum repeater is so difficult because now already more than 20 years passed, so we still not yet succeed. Then we say I need to find a better way. So actually, the more efficient way is to implement satellite-based quantum communication. This is because, and you know, so the effective thickness of the vertical atmosphere is only about 5 to 10 kilometer horizontal atmosphere. So according to the calculation, 80% of the light can pass through the atmosphere. So, and this is mainly because in outer space, we have no observation of photon, and we almost have no decoherence. Yeah. So to see and whether this is possible, so supported by Chinese Academy of Science in 2003, and we start a 10 years journey for ground test to develop all kind of technology to see whether possible really to construct a satellite. So I mean, and in 2005, and here is in Hefei City. Here is the Dasu Mountain. Here is the campus of UTC. Here is a small village, and we managed to verify the quantum entanglement can still survive after penetrating the allosphere. Then, I mean, by 2012, and we really, try to develop all kind of technology to show the high loss satellite to ground channel, is still good enough to achieve satellite to ground QKD. Yeah. So after all these efforts, so in 2016, August, we launched the first missile satellite in Jiuquan Satellite Launch Center. So and this all of you already very familiar for this piece of work. So first, and we try to demonstrate and a satellite to ground and key distribution. Then in experiments, the final key rate is about 100 kilobit per second. So the efficiency is 20 order of magnitude higher than using fiber channel at 1,200 kilometers. Then we also, through the international collaboration, and between Austrian Academy of Science and the Chinese Academy of Science, we managed to show by using the satellite as trusted relay, we can really achieve a quantum key distribution between Vienna and Beijing. So now, and we are also in collaboration with South Africa and Italy and India and also Canada. And in this way, we hope to find out or to test the visibility to establish a global or intercontinental quantum key distribution and network. So, thanks to the pioneer, protocol by, Gilles and Charis and also many others and effort. Now I would like to mention, so now in China, and probably, and all of you know the Beijing, Shanghai, and backbone, which is with the 2,000 kilometer fiber. But now, with all this line, altogether, and the total length already exceed 10,000 kilometers, which is established in 2022. So now, together with and microsatellite, and we already have a space-ground integrated large-scale quantum communication network. So currently, already providing quantum communication service for nearly 5 million users through China Telecom company. Yeah. Okay. So I'm going to finish and very soon. So interestingly, along with the quantum communication and many technology of coherent manipulation photon have been developed, such as I just mentioned, interference of independent photon, interference of single photon, and also high precision of phase stabilization, and also near unity efficiency single photon detection, and also precise frequency and time dissemination. So all these technology together are also enabling quantum information processing, such as optical quantum computation. So it means, as shown by Kinnear, Lafland, and Milburn in 2001. So this show linear optics is sufficient for efficient quantum computing and with the help of multi-photon state. So the multi-photon interferometry technology received from experimental quantum key distribution and quantum teleportation, and already and witness and the development or the growing. So already significantly push the scale of multi-photon interferometry, and which already expand from a few photon to more than 100 photon in the past 20 years. So by which is already good enough to show the demonstration of strong quantum computation advantage and with photon. So in 2020, and we reported the first quantum computation advantage use photon, and to demonstrate the quantum computation advantage and for the Gaussian boson sampling protocol. So very recently, we just submitted this paper, and we already in the Jiuzhan number 4, and so Caoyan Lu and with his colleague, already detect up to 3,000 photon. So now the advantage ratio is up to 41 order of magnitude. So in this way, so advantage, quantum computation advantage has been well established. So now I will mention some future prospect to conclude my presentation. So and in the future is foreseen and to establish a quantum communication network or quantum network. So as we all know, thanks to the MDI QKD protocol, especially the twin beam MDI QKD protocol. So actually, the fiber-based metropolitan quantum communication network already mature and practical. Yeah, and because by using twin beam MDI QKD, one can easily generate maybe 1,000 kbit per second over 200 or 300 kilometers. So which already good enough and within a city. Yeah. And also, as I just mentioned, we already have some, and lovely, progress in the building block of quantum repeater. So the deterministic entanglement distribution over 1,000 kilometers and is expected to be implemented and within 5 years. Then maybe, after another 5 years, then we could really to show some, practical application of quantum teleportation by connecting and distance quantum computer. And also, for the long-distance quantum communication, we will need quantum satellite. So the satellite, still have several problems remain to be solved. So one of the challenge is only using a single LEO satellite cannot cover the whole Earth directly. So the efficiency is quite lower. So one of the possible solution is to construct a high efficiency quantum constellation. So it's some sort of satellite network. And so with an LEO satellite and also GEO satellite, because the GEO satellite could have much longer mooring time, so that we can distribute many more key between two fixed points. So one of the pre-requirement is to ensure the satellite can work under the solar radiation background. So actually, 80 years ago, and Sun Kai, together with his colleague, they already managed to show, the visibility of QKD in solar radiation background. So for the GEO satellite, we will ensure it's possible to perform daylight QKD over 10,000 kilometers and distance from satellite and to the ground. So another thing is, and we need to develop low cost and lightweight microsatellite. Probably, and my colleague already mentioned this and yesterday. So you can see, I mean, so the payload and of missiles, so the weight of missile payload is about 250 kilograms. But now is only for the Jinan number 1 is only 20 kilograms. And also for the ground station, so the weight has been reduced from 1310 to less than 100 kilograms. So by combining both together, lower cost and lightweight microsatellite and portable ground station are within the reach of the current technology. So therefore, in this year, we already show the quantum key distribution with the microsatellite and portable ground station, and on the order of 1 and megabyte keys per orbital. So now I mean, collaborating with the Chinese Qualcomm and the China satellite network, we are currently developing 3-2 quantum microsatellite and to control practical quantum constellation, which is going to be launched probably sometime, and the next year. And also, according to a news report in this March, and around dozens of quantum satellites currently are being developed and prepared for launch worldwide. So for them, ESA and Boeing and so on. So also, the first GEO quantum satellite is currently under development, and which is scheduled to be launched around 2027, in the end of 2027, or at latest in the summer of 2028. Yeah. So, and that's one thing. So the interesting thing is, so the large-scale quantum communication network also provide a new platform for the study of quantum metrology. So as suggested in this interestingly theoretical paper, and this I mentioned with the integrity distribution of the GEO satellite, if we can and store the entangled photon to the atomic quantum memory, then we can enormously increase the the precision of atomic clock. And also, and you can see, and upon the successful launch of our GEO satellite, we are going to achieve integrity distribution on the order of 10,000 kilometers. Yeah. And moreover, and thanks to those technology developed in an optical atomic clock, and which could have long time instability up to 10 to minus 19, and also thanks to the free space optical frequency transfer, and which also can reach instability on the order of 10 to minus 19. Then by combining these two technologies together and by using our GEO satellite, we can achieve global precise time information sharing with long time instability up to 10 to minus 19. Then compared to the current microwave time sharing, we can gain a 4 order of magnitude improvement than the traditional definition of 8 AI unit of second. So we hope, upon successful launch of the GEO satellite, we can provide a new definition of the time unit second in the near future. So we will have ground station in Sanya, and also in another place in China. Then we will have one ground station in Europe, one ground station in South Africa. In this way, we can compare the precision of the atomic clock. And interestingly, here's one thing we are working on. I also would like to mention to you. It's really interesting because we can, with the help of quantum teleportation, one can track the so-called quantum enhanced telescope area. So we know for the traditional very large, light, okay, VLTI, okay, very large telescope interferometer. And so now the best result, so baseline is about, 100 meter. But then, assisted with the quantum teleportation, and because one does not need to send the single photon. So in this way, we can teleport the collect photon from distance telescope to the central station to get the imaging. So therefore, assisted by long distance quantum teleportation, one can achieve interference without directly transmitting starlight, such the length of baseline can be greatly increased, as suggested in this piece of work. So currently, in the nice place in Xinjiang, we call it Altai, and which is very close to the border of Mongolia and Kazakhstan and Russia. We're working on quantum enhanced telescope area, but for the first step, we will only try 1 kilometer diameter. So in this way, we can really provide a very useful method for actual physics. Okay, so this is my last slide. So also we have ambitious plan, and because upon the success of our GEO satellite, so by 2035, we're going to launch another to the deep space, another 2 satellites, and each will carry a ultra-precise optic and clock, which could, and we will try our best to reach the fraction instability 10 to minus 21. So in this way, we can provide a new method for the detection of gravitational wave for the 0.1 hertz and along this and frequency. So which will be a very good compensation to LIGO and LISA, because LIGO and LISA cannot see this area of wavelength. So we can provide a completely new probe for detection of gravitational and wave. Okay, so to conclude my talk, I would like to cite a Chinese and poetry. 复如东海，寿比南山，老亦复利，志在千里. So I already transfer, and translate Gilles to English. Okay, so here it means long-lasting southern mountain. So it's like eastern sea. So here means an eastern sea, 东海. So here means a southern mountain. So happy birthday and all the best, Gil.